Hello, so in this video we are going to talk through this idea of Bayesian statistics. And I'm going to start off with a little quote again, which is, "It's hard to find anything that doesn't advocate a Bayesian approach." Now, Bayesian statistics is really the mathematical way of learning. And there are really two types of people. You're either on the side of the Bayesian statistics or you're on the side of the frequentist statistics. And the idea is, a frequentist statistic is all about making assumptions based on the number of times that something happens. So the more that something happens, the more you can base your assumption on that happening in the future. Okay. Whereas Bayesian statistics is slightly different in that you come up with a hypothesis, you come up with something that you believe to be true first of all, then you collect some new evidence, and then you update that belief based on the new evidence. Okay. And we're going to look at this in a little bit more detail now. So, first things first, I want to start with a little thought experiment. So let's suppose you wake up one day, you're feeling really awful, like you've got a throbbing headache, you've got a sore throat, nose is running, like you're just feeling like absolute death. And you're not quite sure what's wrong with you, so you decide to go to the doctors. Okay, and so you go to the doctors and they look at you and go, well, it could be this, it could be this. They're not quite sure what's wrong with you either. So they go, they take a few tests, and then basically a test for this really rare disease comes back positive after they've taken all these tests. Okay, now this really rare disease is really nasty. You definitely don't want it, right? It only affects 0.1% of the population. So you kind of being a statistician, you go, well, hang on a minute, the chances that I actually have this disease is really low. Like if it only affects 0.1% of the population, it's highly unlikely that I will actually have this disease. So being a statistician, you ask the doctor, what is the accuracy rate for this test? And the doctor tells you that it's 95% accurate. So my question to you is, what is the probability that you actually have the disease then? So you've gone to the doctor. Okay, you've tested positive for this really rare disease that only affects 0.1% of the population, but you know that the test is 95% accurate. So it's not completely accurate. Okay, there is still a chance that you may actually not have the disease at all, even though the test has come back positive. That's what the 95% accurate means. 95% of the time, it will give you the correct result, but 5% of the time, it will give you the wrong result. So using this information, what is the probability that you actually have the disease? And I want to give you four options. It can either be 100%, 95%, 9.5% or 2%. And ordinarily if I was in the classroom, I'd get you to hold up the number of fingers corresponding to the answer which you think it is. Obviously, I'm not going to get you to do that, but I do want you to pause for a second and just think, what do I think the answer should be? Like intuitively, what does it make sense? So disease affects 0.1% of the population. The test is 95% accurate. So therefore, what's the probability that you actually have this disease? Well, the answer is quite surprising. It's actually 2%, okay? And certainly when I first looked at this, I thought, what? That doesn't make sense. But I'm going to show you why it makes sense intuitively now. So these are the two bits of information that I asked you to focus on. That it affects 0.1% of the population and the test is 95% accurate. So using this information then, we should be able to determine this. So let's first of all focus on that first bit of information. The disease affects 0.1% of the population. So what that means, 0.1% means 0.1 in every 100, that's what the percent means. Or kind of if we want to scale this up, it could be 1 in 1,000. That's what 0.1% means. So it means if I take 1,000 people, and I put 1,000 people on the screen there in front of me, one of those people should be affected by the disease. Okay, so 1 in 1,000 people. And here's that poor person here right now. Okay, so here's that little poor person. Okay. Now if I focus on the 95% accurate, it means two things. It either means it's correct 95% of the time, so the test is giving the correct result 95% of the time, or it's wrong 5% of the time, which means that 5% of the people are told that they have the disease, even though they are perfectly healthy. Okay, so just sort of to recap, 95% accurate means that the test is correct 95% of the time, but it then means that it's wrong 5% of the time, which means that of these remaining people, 5% of them are told that they have the disease, even though they are perfectly healthy. So if you look at the 1,000 people, 5% of them should be told they have the disease even though they are perfectly healthy. That's what the 95% accurate means. So 5% of 1,000 is 50, which means that 50 people are told that they have the disease even though they don't. Okay, that's what the 95% accurate means. So what I've got here on the right hand side is 1,000 people. Shaded in blue is the one person who should have the disease. Okay, that's what 1 in 1,000 people mean. That's the one person that actually has the disease. Everybody else doesn't have the disease. However, because the test is only 95% accurate, which means 5% of the time is inaccurate, that leaves 50 people in this original 1,000 who are told they have the disease even though they don't. Okay, so really if I remove all the black people, all the people that I'm not interested in, and just left with the blue people and the pink people, that gives me 51 people in total. One of these people actually has the disease, 50 of the people don't. So therefore, the probability that you actually have the disease should be 1 in 51, okay, which is about 2%. Okay, so 1 in 51, which is about 2%. Okay, so that's the probability that you actually have the disease if the test comes back positive. That's what the whole 95% accurate means. Now, like I say, this doesn't really make sense. Like intuitively, when you looked at those answers, you probably weren't thinking 2% was the chance that you actually have the disease. Like usually you go to the doctors, the test comes back positive, and you think, oh, okay, this means that I probably have the disease, particularly if it's 95% accurate, right? But it's not the case. There's actually only 2% chance that you have the disease, right? So really, this gets to the heart of what Bayesian statistics is all about. That thought experiment gets to the heart of what we're talking about here. And it's basically a way of updating our view of the world based on new evidence that comes to life. And I really like this quote: we are the sum total of all our experiences. In other words, as you go through life, you become more experienced, okay? And you've managed to update your view of the world lots and lots of times because of the evidence that you've come across, okay? The longer you live on the world, the more wise, hopefully, you become because you've updated your view of the world based on that new evidence, okay? So, let me give you another example of where Bayesian statistics could crop up. It's a slightly different example. Now, apologies for on the screen. It's because I've got the green screen going. So these should be nice green rolling hills, and these trees should be green as well. But unfortunately, the chroma key has cut those out. But I'm sure you'll still get the idea. So let's imagine that somebody has been living in their cave all their life. They've never emerged from their cave. They've always been living underground like a little mole, okay? And then one day they decide, I'm bored of this cave, I'm going to go outside. And it's the first time they see the world. So they come out to their cave, they look up, and then they see something amazing, okay? They see this great big ball of light in the sky coming up, okay, and shedding light over the entire area. Now this is the first time, you remember they haven't been out their cave in forever. This is the first time they've seen this event happening. So the first time they see it, they think, wow, this is like some really rare natural phenomena. I've never seen this before. Like it's beautiful, this big ball of light coming up through the sky, okay? But then they stay outside and then it sets again. And then the next day it happens again, okay? And then the day after that, guess what? It happens again, okay? And basically after a few days, it keeps happening. So this thing which they thought was a really, really rare phenomenon actually just keeps on happening over and over and over again. Now, what do you think this caveman is now thinking? So at first he thought that this phenomenon, this sort of light, great big ball of light coming up in the sky was a really rare phenomenon. They thought, he thought it just by pure chance, the day that he came out of his cave was the day that he saw this really rare phenomenon. But then it kept happening. So what do you think that caveman is now thinking? Do you think it's still a rare phenomenon? Well, probably not. And this is an example of Bayesian statistics, right? He thought at first it was a really rare phenomenon, this ball of light coming up in the sky, and then it just kept happening. And then he's like, well, actually, it's probably not a rare phenomenon anymore. It's probably something that happens quite a lot, okay? Another example of where this could be used. Let's suppose you're walking around the university campus, okay? And you know that this student that you see is either a member of a business department or the maths department. And they're walking around campus and they've kind of got their head down, they're really shy, not really engaging, not really making eye contact with anybody, not talking to anybody. So you know that this really shy student is either a member of the business department or the maths department, okay? Now, first thoughts, which department do you think this student is a member of? Do you think they're a member of the business department or do you think they're a member of the maths department? Well, because mathematicians generally have this reputation of being quite sort of shy, quite introverted, not really wanting to engage with people, kind of keeping themselves to themselves, you may think at first thought this student should be a member of the maths department. But let's actually look at the evidence and see if we can update that view of our world. Okay, so let this box represent every single student within the main campus. Okay, and you know that on main campus, 80% of students are in the business department, but only 20% of students are in the maths department. So the maths department is a smaller department overall. It's only got 20% of the students. Okay. By the way, let's just assume that the campus has only got these two departments, just for the sake of simplicity. Okay. So you know that there's a higher chance, if you didn't know anything else, you knew that there's a higher chance that a student will be in the business department than the maths department because the business department is bigger. It's got a higher proportion of students. Okay. So at the moment, and this is what we're going to call our prior ratio, this is basically the thing which we believe at the start, is 80 to 20. In other words, 80% of students are in the business department, 20% of students are in the maths department. But then let's maybe update our view of the world. So let's maybe ask a survey of every single student, and maybe it's a survey which can determine their personality. Okay, and we're able from that to determine whether somebody is shy or whether somebody is quite extroverted. All right, so let's do this, and the results of the survey, so apology about the top bar, but the results of the survey show that 20% of the business students are shy, whereas 60% of the math students are shy. So this is still kind of making sense, right? So there's more, you know, the vast majority or the proportion of the math students are shy. So there's a big majority of the math students which are shy, whereas a much smaller proportion of the business students are shy. Okay, so therefore what we can do is update this ratio based on this new evidence. Okay, so this is what we're going to call the likelihood ratio. This is basically our new evidence which we're interested in. And again, 20% of the business students are shy, whereas 60% of the math students come back as shy. So what we need to do now is work out how to combine our prior ratio. Remember, our prior ratio was a thing which we knew at the start, okay? That was the proportion of students which were in each department. Then the likelihood ratio is our new evidence which comes to light. Okay, so our new evidence in this case is the proportion of students in each department that are shy, okay, which we've got as 20 to 60. So really what Bayes' theorem is all about is it's a way of comparing the size of the two shaded rectangles, because this is the proportions of each student that we're interested in. We're interested in shy students because we see the student walking around campus, we know they're shy. So we're interested in the shy students and we just need to compare the proportion of each of these bars, okay, and that will give us which student it's more likely to be, which student the student that we see, which department are they more likely to be in, okay? So if we compare the size of the two bars, okay, we work out that actually there are more shy students in the business department on campus than there are shy students in the maths department on campus, which means that there's a higher chance that this shy student that we see walking around campus is a member of the business department. Now, if you think about it, this kind of makes sense, right? Because if you only have like 2 people in the maths department, but whereas if you have 8 people in the business department, then there's a far more, you know, and there's a bigger chance that the student is going to be a member of the business department than the maths department anyway. That's our prior ratio, okay? But then the likelihood ratio kind of gives us extra evidence with this. And it basically says, well, actually, because 20% of the students in the maths department are shy, the business department are shy, and 60% of students in the maths department are shy, well, if you think about it, if there are 8 students in the business department, but only 2 students in the maths department, then 20% of 8 is still bigger than 60% of 2. Does that make sense? So 20% of 8 is still bigger than 60% of 2. Therefore, there are more students on campus that are shy and are members of the business department than there are students on campus that are shy and members of the maths department. Okay. So actually, this does kind of make sense, and it's a way of just emphasizing our view of the world. But the point which I want to get across, you start off with the prior ratio. That's the thing which you believed at the start. In this case, it's the proportion of students on campus that are a member of each department. Then you bring in this new evidence, which we're calling the likelihood ratio, and that's basically the proportion of students within each department that are shy. So how are we going to combine these together? Well, because it's area, we should multiply them together. And this will give us the posterior ratio. Now, posterior just means behind. It means after we've considered all the evidence, so our prior ratio, that's our initial belief, and the likelihood ratio, that's the new evidence. After we've considered these two things together, we get our posterior ratio. That's our new belief. Okay, and because we're working with areas, it makes sense to multiply these things together, right? So we're multiplying 80 by 20 and 20 by 60, and we get 1600 over 1200, or we can simplify that down to 4 to 3, which means that 4 in every 7 students should be in the maths business department and they're shy, and 3 in every 7 students are shy and members of the maths department. Okay. So in other words, the chances of this student, there's a higher chance that this student that we see wandering around campus, really shy, introverted, keeping themselves, not really making eye contact, not really engaging with people, there's a higher chance that that student is a member of the business department, okay? Okay, fine. So really the thing which I wanted to get across here is the idea of these 3 ratios. You first of all got the prior ratio, that's your initial belief. Then you have your likelihood ratio, that's the new evidence. And when you multiply those 2 things together, you get your posterior ratio. That's your new belief based on the evidence which you've considered, okay? So, this kind of idea is also seen quite a lot in forensic statistics, and this is the last example that we're going to look at of Bayesian statistics. So forensic statistics is all about looking at the chances of something happening, considering evidence in a quantitative and sort of a rigorous way, okay? So let's suppose that a crime has been committed. And we know that there are 1,000 possible perpetrators. There are 1,000 people who could have possibly committed that crime. Perhaps there's 1,000 people who were in the area when that crime was committed. So we know there's 1,000 people who could have committed that crime, okay? And then let's suppose an unreliable witness comes forward. Perhaps this witness was perhaps drunk, or perhaps they didn't quite see things properly, or perhaps they didn't quite remember things properly. So they're unreliable, but nonetheless, they did see the crime being committed. So they are a witness, okay? And let's suppose they point out a particular suspect and they say, I think I saw this person committing the crime. But like I say, they're unreliable, okay? So in other words, our prior belief, a prior ratio, if you like, is that this student, or this, well, let's say this criminal, could be a student, but let's suppose this criminal was the one who committed the crime, okay? So therefore, the prior ratio will be 1 suspect in the original 1,000 who could have committed the crime, okay? So the prior suspect, the chance of them committing the crime is 1 in 1,000, okay? All right, now let's suppose some new evidence comes to life. And actually in forensic statistics, the most common type of new evidence is actually DNA evidence. So let's suppose DNA evidence is found at the scene of the crime, okay? That's spelled wrong, my apologies. That shouldn't be seen, it should be S-C-E-N-E, okay? And let's suppose that this DNA evidence actually matches the suspect that was originally pointed out. So this suspect that was pointed out by the unreliable witness, let's suppose that the DNA matches that suspect, okay? Now, is that enough to make a conviction? Well, no, not quite, because you need to form a likelihood ratio based on the chance that this evidence is just matched by pure chance, okay? Now, just to kind of give you a bit of an idea here, DNA evidence is effectively a genetic mutation, okay? So DNA is effectively genetic mutations, okay? And the thing is, in the world, there are, I think, about 7.8 billion people at the moment, as of this video being recorded. And so just by pure chance, there should be people on the earth who have exactly the same DNA sequencing to you. It's very unlikely, but there is a chance, okay? Because there's 7.8 billion people in the world, suddenly if it's like 1 in a million, that's a small chance, but if you scale that up to 7.8 billion people, suddenly that means that more than one person should, by pure chance, have the same DNA evidence. And so this is why we need to consider the likelihood ratio in this particular example, okay? So the likelihood ratio, it's a bit wordy, but let me talk you through it. It's basically the probability of getting a DNA match, assuming the suspect actually committed the crime. Okay, so what's the probability that you'll get a DNA match, assuming that the suspect actually committed the crime? Then you need to compare that, so you need to give it as a ratio, with the probability of a DNA match, assuming somebody else committed the crime. In other words, you just get a pure DNA match just by pure chance, okay? Well, okay, this thing on the bottom is called the random match probability. So the probability that you get a DNA match just by pure chance, even though the suspect didn't commit the crime, their DNA is matched just by pure chance. That's called the random match probability. And you need to consider it in forensic statistics, okay? Because there is a chance. You've also got to consider sort of how clean the DNA evidence is. Perhaps it's been sort of found in a public toilet, for example, where there's lots of kind of DNA evidence all around the place, which is a bit, ugh. But yeah, there is lots of DNA evidence, so it may have been contaminated. It may have also been that the DNA evidence hadn't been collected properly. Okay, so there wasn't enough there to get a true match. Okay, so only a partial match, right? So you need to consider all these things when you're considering the random match probability, and this is what forensic statisticians do. Okay, so let's suppose, well, obviously the probability of a DNA match, assuming the suspect committed the crime, that should be 1, that should be certain, okay? If they actually committed the crime, then the DNA should match, okay? Then therefore that's 100% certainty, hence I've just put 1 there. But let's suppose that the probability of a DNA match, assuming that somebody else committed the crime, was 1 in a million. Okay, 1 in a million. Well, that means that if there's 66 million people in the UK, for example, that 66 people should have exactly the same DNA to you. So in other words, this DNA sequence should match 66 people in the UK. And it may be that 2 people were in the same area who had the same DNA match. Okay, so it may not necessarily belong to this suspect. Now, actually, you know, there's been quite a lot of talk about this random match probability, and they now say that if it's sort of 1 in a billion, that you can actually just make a conviction on DNA evidence alone. You don't have to consider any other evidence, but you know, that's another story. So now if we look at 1 divided by 1 in a million, okay, that's the likelihood ratio as a million, okay, and obviously you want this likelihood ratio to be as high as possible. The higher the likelihood ratio, the more chance that this suspect actually committed the crime based on this DNA evidence. So now what we need to do is actually put these 2 things together. So if you remember right back at the beginning, I said the prior ratio was this 1 suspect in the 1,000 people that could have possibly committed the crime. The likelihood ratio, well, we've just worked that out, okay? It's the probability that the DNA matched the suspect, and you need to consider that in relation to whether they, just the random match probability, whether the suspect just gets a random match to the DNA just by pure chance, okay? So when you multiply this together, you get 1,000, and obviously the idea is that the higher the number over on the posterior ratio, the higher the number over here on the right, the more probable that the suspect committed the crime. This is really an introduction to forensic statistics, but it's using this idea of Bayesian statistics. You're taking a prior ratio, you're multiplying by likelihood ratio, and then you get your posterior ratio. And the higher the posterior ratio, the more likely it is that the suspect committed the crime. Now, in actual fact, this kind of idea here, the idea of likelihood ratios in UK court, you can give evidence and you can talk about likelihood ratios in UK court, but in actual fact, you can come up with a prior ratio, you can come up with a likelihood ratio, you can present them both separately, but you can't multiply them together. The actual act of multiplying them together in UK courts is banned, and the reason being is because there was a case in the 90s, there's a case in the 90s that sort of looks at this, and they ended up completely confusing the jury, and they ended up making what was considered a mistrial, so the conclusion wasn't valid. Okay, so if you're interested in that, then please go away and have a look at that. It's on Wikipedia. But yeah, so basically you can talk about likelihood ratios, but you can't multiply anything. You can't do that. And in fact, you can't talk about the prior ratio or the posterior ratio. So you can talk about the chance that the DNA evidence actually matched the suspect. That's fine. The likelihood ratio is fine. But you can't talk about the prior ratio and you can't talk about posterior ratio. You can't multiply these things together. Okay. So in other words, the maths doesn't work. Okay. And if you did want to have a look at that, there's a link there which I strongly recommend you have a look at. That's a real life example in the UK. Okay. Okay, fine. So we've already done this in class. So effectively, we've got a table here, and we have to fill this table in. And I've basically got 2 categories, whether you're male or female, or whether you're statistics or like maths. Okay, so let's suppose we have a table that looks like this. So let's just suppose this is the table that we've got, okay? And I've just filled this out based on sort of some data perhaps I've asked you in class. I've asked you, are you male or female? And I've asked you, do you like maths or stats? Okay, and I've filled this table out. And these numbers correspond to the number of people in each of the rows and columns that like each of these subjects, okay? Now, what we're able to do from here is answer questions such as, well, what's the probability that this person is female? Well, if this person is female, that basically means that basically means that there are 12 females in the class in total. So I want to look across the entire row. There are 12 females in the class, and there are 20 people in the class in total. So therefore, the probability that that person is female is 12 in the 20 people. Okay, which of course I could simplify. And I can also do things like this. What's the probability that the person likes maths? Well, okay, I need to look at the number of people that like maths. So the number of people that like maths are 15, and there's 20 people in total. So the probability they like maths is 15/20. Okay, and I can also do things like what's the probability they're male and they like statistics. Okay, so what's the probability that they're male and they like statistics? Well, there's 3 males who like statistics in the class. Okay, there's 3 males who like statistics, and there's 20 possible people in the class. So therefore, that should be 3/20. And I can also do things like what's the probability they're female, or they like maths. Okay, so as an example, what's the probability they're female or they like maths? Well, hang on a minute, we need to look at the total number of people who are females. So we need to look at all of the people who are either female or they like maths. Okay, so these 2 people here are female. They like stats, but they're female. They want to include them, right? These 10 people here are females and they like stats. They satisfy both of those. That's totally fine. So I want all of those 10. Okay. But I also want these 5 males, because these 5 males, even though they're not female, they like maths. So I just want people who are either female or they like maths. So in total, there is 2 plus 10 plus 5. That gives me 17 people in total who are either female or they like maths. And there's 20 possible people in the class. Okay, so the probability they're female or they like maths is 17/20. Okay. Now what I can do now is actually introduce this idea of a conditional probability. Okay, so if I say, for example, what is the probability of event A happening given that B has already happened? Okay, so what's the probability of A happening given that B has already happened? The way which I would write that is the probability of A, and I'd use this vertical line here to represent given. It's conditional on B having happened, and you always read from left to right. So this is the event you're interested in, but it's given on event B having happened. That's the way to interpret it. So as an example, if I ask for what's the probability that a student likes maths given that they are male, okay, well I can come up to my table now and I'm only going to be looking at those people that are male. Okay, I'm not interested in the females at all in this case because I'm given that this student has to be male. So I need to look at that row of my table. So in other words, the 8 people in total, okay? And I'm looking for the probability that they like maths of those males. Well, there's 5 males who like maths. So therefore the probability that they are male and they like maths has to be 5/8, okay? If I want the probability that they like stats, given they are female, okay? In fact, let me do it the other way around, okay? Let me do the probability they are female, given they like stats. Well, in this case, I'm going to be looking at people who only like stats, okay? I'm going to be looking at only people who only like stats. So that's this column here. These are the people that only like stats. And I want the probability that they are female. Well, there's 2 of the original 5 people that like stats who are female. So therefore the probability down here will be 2/5. Okay, so hopefully that makes sense. Okay, this given probability, this conditional probability is basically saying what is the probability of something happen given that something else has already happened. Okay, now let's go back to our PowerPoint slides, and there's 3 really important key terms that I want to define here. They are independent, dependent, and mutually exclusive. Now, independent basically just means that if one thing happens, it doesn't affect another thing happening at all. Okay, so basically one event happening does not influence the other event happening. So you can see here I've used my conditional notation. It's basically saying the probability of A happening given that B has already happened should be exactly the same as probability of A happening given that B has not happened. That's what the dash means, it's not happening. Because in this case it doesn't matter whether B has happened or not, the probability of A should be the same. Remember that one event happening doesn't influence the other event happening. So whether B has happened or not, it doesn't influence the probability of A happening. Therefore, it's independent. So as an example, you could talk about rain and day of the week. Okay, so whether it's raining or not is not influenced by what day of the week it is. Okay, dependent is the exact opposite. Okay, so dependent means the chance of one event happening depends on another event having happened. So therefore, in this case, it's exact opposite of this. The probability of A given that B has happened will not necessarily be the same as the probability of A happening given that B has not happened. In other words, the chance, whether B has happened or not, it affects the chances of A happening. And this is where conditional probability really comes on. It's dependent on, it's given that something else has already happened, the probability of A happening will change, okay? Last thing I wanted to find, the example here, wearing a coat and snowing, right? So where, the chance of you wearing a coat is dictated by whether it's snowing or not. So if it's snowing outside, that's going to influence the chance of you wearing a coat, okay? Notice as well here in this case with this example, these two things are not interchangeable. So whether it's snowing or not is not dependent on whether or not you're wearing a coat. Okay, those two, there's a little subtle difference. So the weather doesn't decide whether to snow or not just because you're wearing a coat. Okay, whereas you deciding whether to wear a coat or not is dependent on whether it's snowing or not outside. Now, last definition, mutually exclusive, nice and simple. Exclusive means it's only happening here. Okay, and mutual means together. So if you put all that together, it basically means if one event happens, the other event can't happen. So I'm using this special notation here, okay? The and notation I can write as the intersect, which is this little upside down U. So the chance of A and B happening, in other words, both things happening, is 0 if they're mutually exclusive. So as an example, turning left and turning right. You can't turn left and turn right. You can turn left, which means you're not turning right, or you can turn right, which means you're not turning left. You can't do both, okay? So what we can do now is take our two-way table, which we did in the last, just a minute ago, and we can turn this into a tree diagram. Now, a tree diagram is a really lovely way of representing outcomes. Now, two-way tables are great. Okay, so the two-way table that we just did, they are great, but they have their limitations. And the main limitation is that it only works if you've got two particular conditions, okay? So if you've got only two particular categories. So in the case which we're looking at, we looked at, are you male or female, your gender, do you like maths or stats, so what subject you prefer. So we're looking at two different categories, two-way tables are fine. But if I want to now introduce another event, for example, your age, okay, so whether you're over 25 or under 25, then two-way tables will now start to fail, or you'll have to be quite clever about how you set up the two-way table. Whereas a tree diagram, no issues with it. So a tree diagram is very, very particular in how you set this up. Effectively, each branch represents a particular event. So if you look here, I've grouped the first set of branches together, okay? And this basically represents what gender you are. And each branch represents a different event. So you can either be female or you can be male, okay? And the probabilities for each go on the branches. So you can either have the probability you're female, and then down here will be the probability that you're male. But then from that, you can then follow along and see what the next kind of outcomes could be. So the next outcomes are what gender you are. Okay, so if you're sitting here, if you're female, then you can either like statistics or you'll like mathematics, okay? And likewise, if you're sitting down here, you're male, then you can either go on to like statistics or go on to like mathematics. Now notice the probabilities in this case have to be conditional. So this probability up here is not just the probability of statistics, because this probability up here should be different from this probability down here. Remember, they're dependent probabilities. They're conditional on what's just happened. So this probability up here is not just probability of statistics, it's the probability of liking statistics given that you are choosing a female. So given that you are female, okay? Whereas down here, the probability of liking statistics should be dependent on whether you're male. Okay, so your probability of liking statistics given that you're male. And likewise, this probability here is not just the probability of liking maths, it's the probability of liking maths given that you are female. And this probability down here, again, should be the probability of liking maths given that you are male. Okay, so in which case then, I think we can fill out this particular tree diagram using our two-way table. So here we've got our two-way table in the top left corner, and I've just drawn out a blank tree diagram down here. And my job is to put the probabilities along the branches. So let's first of all select the probability that goes here. Now this is just the probability that this person is female. So chance that they're female, well, there's 12 females and there's 20 students in total, so therefore it's 12 in 20. Okay, and the probability that goes down here, well, that's the probability that they're male. Well, there's 8 males and there's 20 students in total. So therefore, there's 8 in 20 students that are male. So probability that the student is male is 8 in 20. Okay, now you notice first of all that if I just look at this particular group here, that probability, so if I add this probability and this probability together, that probability should add up to 1. Okay, so 12 20ths plus 8 20ths should add up to certainty. Should add up, because I'm either going to be male or female. Okay, Now let's go on. So let's choose this thing up here. Okay, so this probability up here. Well, this, remember, is the probability of liking statistics, but it's not just the probability of liking statistics, because it's the probability of their liking statistics given that they are female. Okay, so because you've just chosen a female out now. So I'm only going to be looking at the females, and I'm going to be looking at the number of females that like statistics. Okay, well, there's 2 females that like statistics, and there's 12 females in total. So it's 12/20ths. Okay, this probability down here is not just the probability they like maths, it's the probability they like maths given that they are female. So therefore, again, I'm just looking at the females up here. There's 10 out of 12 students that are female who like mathematics. Okay, so probability of liking mathematics given you're female is 10/12. Now, if I look down here at this probability, well, this probability is going to be probability of liking statistics given that they are male. So now I'm looking at the males. Okay, now I'm looking at the males. There's 8 males in total, and 3 of them like statistics. So therefore, it should be 3/8. Okay, and then the probability down here, well, this probability here is going to be the probability they like maths given they are male. So therefore, there's 5 male students who like maths, and there's 8 male students in total. So it's 5/8. And again, look at the probabilities of the branches. They add up to 1, and they add up to 1 as well. So just a quick check to do there. Now, what about these probabilities that go here? So it's basically a probability at the end of the branches, and these probabilities represent both events being happening. So this would be the probability that they are female. In fact, so I'm just going to write, female. And, so I'm going to use that notation there, they like stats. Okay, so this is the probability they're female and they like stats. The way to calculate that probability is by multiplying the probabilities on the branches that you've had to go along to get to that point. So 12/20ths multiplied by 2/20ths, that's going to give me 2/20ths. I'm just going to leave it as 2/20ths for the time being, and you'll see why in just a second. This probability here is going to be the probability that they like, that they're female and that they like maths. Okay, so this is the probability that they're female and they like maths. So therefore, in order to calculate this probability, I need to multiply the probabilities on the branches. Okay, so it's going to be 12/20ths multiplied by 10/12ths. That's going to be 10/20ths, or 1/2 if you prefer. Okay, really good tip when you're dealing with tree diagrams, don't simplify it until the very last minute. So only when you're over here should you end up simplifying. But I'm actually just going to leave it like this for the time being, just to show you what's going on. Now this probability here is going to be the probability they're male and they like stats. Okay, because look, I've had to come along this branch and then this branch. So in order to calculate that, I'm going to have to multiply the probabilities together. So 8/20ths multiplied by 3/8, that's going to give me 3/20ths. Okay. And then finally, this probability here is going to be the probability they're male and they like maths. Okay, so this probability is going to be 8/20ths times by 5/8. That's going to give me 5/20ths. And you notice as well, same as before, if I add together all of these probabilities, what do they come out as? They come out as 1. Okay, so they all come out as 1. All right, so that's really important. Okay. Now, why is this important? Well, it means now that I can basically derive Bayes' theorem. Okay, so Bayes' formula. So let me show you. Okay, let's just simplify this. So instead of having like female and male, I'm just going to call it event A and event B. And actually, I'm going to just put the probabilities on here. So this will be probability A, probability B. And I'm just going to repeat the same branches again. Okay, so if event A happens, it can totally happen again, or I can have event B the second time. Okay, so this will be the probability that B has happened given that A has already happened. So this branch down here will represent the probability that B is happening given that A has already happened. And likewise, if I do the same thing here, this branch will be the probability of A happening, but it's given that B has already happened. Okay, so if I try and relate this back to Bayesian statistics, because we're kind of taking a little bit diversion, you're probably going, well, what's this got to do with Bayesian statistics? If you like, I can work out the probability of A and B both happening. So on the left-hand side, this first set of branches, if you like, our previous belief. This is the belief that we started with. This is our prior ratio. Okay, this is the thing which we started with. You can either have this or you can have this. Okay, that's the previous belief. You then update that based on new evidence, and this is what the second set of branches represent. Okay, so this is our new evidence. And obviously over here on the right-hand side, I can work out what that new evidence is to get my posterior belief, almost. Okay, So therefore, if I wanted to get probability of A and B here, I'd have to take the probability of A and times it by the probability of B given A. I'm just literally multiplying the probabilities on the branches. Likewise, to get the probability of A and B here, I'd have to take the probability of B and multiply it with the probability of A given B, okay? So in other words, I have two ways of working out the probability of A and B happening. It's either the probability of A times by the probability of B given A, or is the probability of B given times by the probability of A given B, okay? So if I just look at these two formulas, they're completely equivalent, they should be equal to each other, okay? I could basically set these two things equal to each other. So I take these two formulas, set them equal to each other, and I get this, okay? Now if I just want to do a little bit of rearranging, let's suppose I want to work out the original conditional probability. What's the probability of A happening given that B has already happened? That's conditional formula, okay? Given that B has already happened, that's the thing you start with, okay? And then you want to work out the probability of A based on your new evidence, okay? So the probability of A given B. So let's rearrange this formula to get the probability of A given B on its own. In order to do that, I need to divide both sides by the probability of B, okay? Now another way of thinking about this, remember that the probability of B given A times by the probability of A, that is just given as the probability of A and B both happening. So in other words, I could write this as simply the probability of A and B. Now this here, highlighted in blue, is Bayes' formula. Okay, remember it's really important formula, but it basically just comes from the idea of just looking at tree diagrams, okay, and just looking at what's the probability of A and B happening. Well, you're looking at the probability of A times by the probability of B given A, or it's the probability of B times by the probability of A given B, okay. So let's come back right to the very start with our disease example from earlier, okay. So we have a disease that affects 0.1% of the population. The test is 95% accurate. That's what we established earlier, okay. Now, we realised at the very start, so I showed you kind of intuitively by thinking about what 0.1% actually means, then what the 95% accurate actually means, like visualising those 1,000 people, okay, and then just picking out, okay, it's basically the chance of being one in these 51 people who have been told they have the disease, okay, and we came out as 2%. But I'm going to show you that you can work out exactly the same thing using this Bayes formula that we've just derived. So if I basically come up with Bayes formula, okay, I need to draw myself out a tree diagram. So my prior belief, okay, is the probability whether you actually have the disease. Okay, that's before you've got any new evidence, before you've taken a test or anything like that. It's just basically what is the probability that you have this disease. Okay, so you either have the disease or you don't. So probability you have the disease is 0.1%. Probability you don't have the disease is 99.9%. Okay, that's your prior ratio. That's your prior belief. Okay. Then you introduce the new evidence, which is that you get the test results back. You go out, you take a blood test, or you get the test results back, and you get some new evidence in that way. So either, based on this test, you can test positive or test negative, given you have the disease, okay? Well, okay, let's have a look at this. If you test positive, given you have the disease, then the probability should be 95%. In other words, the test is being truthful, the test is being accurate, okay? If you're testing positive and you actually have the disease, that is an accurate test result. Whereas if you test negative, but you actually have the disease, that means the test is wrong. That means the test is inaccurate. So therefore, the probability up here should be 95% and the probability down here should be 5%. Likewise, you may not actually have the disease, but the test could still come back as positive. Well, that's the wrong test result. So therefore, that probability should be 5%. Okay, that's an inaccurate test result. Whereas down here, you could not have the disease and you test negative. That's the correct result. So therefore, that probability should be 95%. Okay, so now we've got this set up, I want to work out what is the probability that I actually have the disease. In other words, I know, remember, that I've tested positive. So that's given, I've tested positive. I want to work out what's the probability that I actually have the disease. So I want to work out the probability that I have the disease given that I've already tested positive. Well, if I have a look, if I compare that to Bayes' formula, okay, well, have a look. The probability I have the disease is on the left-hand side. That's where A is in my formula. So in other words, event A should be the actually having disease. And then testing positive is where B is in my formula. Do you see that? So therefore, the event B should be testing positive. So therefore, if I just stick all of that into my formula, so remember B is testing positive and A is having the disease. If I stick all the correct thing in the right place in my formula, I get this on the right-hand side. So now I just need to go through and actually work out what this is. Okay, so let's actually have a look at going through this then. Okay, so first things first, I just need to fill in everything that's in this formula. Okay, so first of all, I want the probability that you test positive given that you have the disease. Okay, well, the probability of testing positive given you have the disease, that's that probability up there, right? That's the probability of testing positive given you have the disease. So that there should be 95%. Okay, so that there should be 95%, right? Then I want to multiply that with the probability that you actually have the disease. Well, just remember the probability that you actually have the disease is basically just your prior ratio. That's the thing which you believe when you start off. That's 0.1%, right? So that there should be 0.1%. Then I need to divide that by the probability that you test positive. Well, are you happy? There's two ways you can test positive. You can either test positive and have the disease, or you can test positive and not have the disease. So just remember, to find out the way of testing positive, you need to multiply this by this, so 0.1% times by 95%, or you need to multiply the don't having disease probability by the probability you test positive in that case, in which case that's going to be 99.9% times by our 5%. Okay, so there's two ways you can test positive. Now, how are we going to combine together those two probabilities, so this one and this one? Okay, well, quite simply, the way to combine them together is using a plus, okay? Because in this case, you're talking about an or. So just remember, in probability, if you're talking about and, in other words, you want both things to happen, you need to multiply those two probabilities. If it's an or situation, in other words, you want one thing to happen or the other thing to happen, you have to add the probabilities. So in this case, you need to add these two probabilities on the basis that you can either test positive and have the disease, or you can test positive and don't have the disease. You can't have both at the same time. You can't have the disease and not have the disease, okay? So therefore, it's adding these probabilities together. So you're going to take 0.1% and you're going to multiply it with 95%. Then you're going to add that to the second probability up here, which is 99.9% multiplied by 5%. And we're going to stick all this in our calculator. So let me show you how you should stick this into your scientific calculator. Okay, so if I just bring up my calculator here, all right. So effectively, I need to start off by actually bringing up my fraction button. So my fraction button is on here. Okay, so my fraction button is here. You see this empty fraction? So I'm going to click that, and it brings up an empty space on the top and the bottom. So I'm going to start off by typing in my numerator. So my numerator, remember, is just 95%. So I'm going to type 95, and then I'm going to use the percentage symbol, which is in yellow up here. So in order to get the percentage symbol, I'm going to have to click Shift and then click on that button there to get the percentage. Okay. Then I'm going to have to multiply that with 0.1%. So I'm going to type 0.1, and again I get my Shift and that button there to get my percentage. Now I need to go on the bottom. Now in order to get on the bottom, I'm just going to press the down button. So this down button there, okay? So to navigate, I'm just going to keep on pressing the key. So I'm going to press the down button, okay? Then I need to type my 0.1%, so 0.1% times by 95%. Plus 99.9% times by 5%. Okay, so times that by 5%. And I'm just going to hit equals, and it comes back as, now at the moment it's giving it as a fraction. That's fine, but realistically I want to leave it as a decimal, or at least as a percentage. So in order to convert this into a decimal, you press this button here, which is S to D. And it basically converts both ways. So if I press that now, that is going to be the decimal. So to convert that to a percentage, it's going to be, well, what's it going to be? It's going to be 0.019, which is approximately equal to 2%. It's 1.9%, which is where our 2% came from in that first instance. Okay, so remember our 2% came from our first instance here. That's where it comes from. Okay. Now, in actual fact, what we've done here is we've used Bayes' formula. Now, where's our prior probability? Well, our prior ratio is this thing here. It's the chance of thinking, do you actually have the disease? Okay, start off with, it was 0.1% that you have the disease and 99.9% that you don't. But now what we've done is we've got our posterior ratio. We've got our new belief, which is that our new belief is that we've got a 2% chance that we actually have the disease. Okay, which means that we're sitting here and thinking, that doesn't seem very confident. That doesn't seem very convincing. So what are we going to have to do to make it more convincing? Well, quite simple. We just do more tests. That's what literally you do in hospitals, right? If you've got a test with only 95% accuracy rate, okay, and it's a low chance that you actually have the disease, at the moment we're sitting on a 2% chance. So are you going to go to your patient and say, hey, you've got a disease and you need to go undergo all this horrible treatment and months of agony and heartache, when there's actually only a 2% chance that you actually have the disease? No, you're going to do more tests, okay? So let's suppose we just do the test again. Okay, do exactly the same test again, take your blood again. And let's suppose now it comes back as positive again. Now what's the probability that you actually have the disease? Well, in order to do that, we need to update our tree diagram. Okay, so now the probability we have the disease, we now think the probability we have the disease is now 2%. Okay, because we've just done a test and it's come back positive, which means there's a 98% chance that we don't have the disease. Okay, which means we're also going to have to update all of these things over here. So that's going to have to update to 2%, and that's also going to have to update to 98%. Which means that I also need to update it in this formula here. Well, this is the thing I need to update. I need to update this, and I need to update this. Okay, so now I've updated my prior belief, I can now work this out again. Okay, so let's see what happens if I work this out again. Okay, so if I work this out again, it should come back as about 28%. Okay, so about 28%, okay? And actually what happens, I can just keep updating my probability because I say, well, actually 1 in 3 chance, again, that's still not a great probability. So let's now update it again, and let's update this to 28%, which means this has got to be updated to, well, what's 28%? That's going to be 72%, okay? Which means this has got to be updated to 28%. This has got to be updated to 72%, okay? And this also got to be updated, so this is 28% now. This is 28%, and this is 72%. Well, now if we stick all of that into our calculator, so now we're doing the test 3 times. Let's suppose now the test comes back as positive. Now what's the probability that we have the disease given we've tested positive, given that we've got a test result on 3 consecutive cases? Well, now if we do that, it comes back as 88%. Okay, this is looking more likely. Okay, and in fact, if we keep going through this, the first test, the first time we didn't have a test. So therefore we walked in there knowing that the chance that we actually have the disease, given that we've got no other information to go off of, was 0.1%. That was just the chance of having the disease in the first place. Then if we update this by doing a test, we find that now if a test comes back as positive, the chance that we actually have the disease is 2%. So then if we do the test again, if the test comes back as positive, we've now got a chance that there's 28% chance of actually having the disease. Then if we do the test again and it comes back as positive, we've now got an 88% chance. And in fact, if we keep going, by the time we get to our 4th test, if that comes back as positive, so we've had 1, 2, 3, 4 tests, all coming back as positive, we've now got a 99% chance of actually having this disease. And if we do it last time, so 5 tests in total, so do this test 5 times, we've now got a 99.9% chance of doing the disease. Now this is the reason why when you go into doctor's surgery and if you have tests, this is the reason why they take so many samples, okay? They do so many tests on you because they want to be sure, well, first of all, they want to actually narrow down what disease they're talking about. But if you actually test positive, they say we need to run some more tests. The reason being is this, it's Bayesian statistics. Just running one test alone is very rarely enough to be confident that you've actually got the disease. So in this case, look at this. I mean, we were only getting relatively confident after about the 3rd or 4th test. And actually by the time we got the 5th test, we're pretty much, yeah, okay, we probably got the disease and we need to start treatment. Okay, so just be aware of that. That's the reason why when you walk into a doctor's surgery, they do sort of multiple tests on you. Okay, so let's actually have a look at an example of a type of question which you could be asked, say, in an exam situation. So let's actually have a look at this example here, okay? So we've basically been told that a factory has 3 machines that are making a large number of components. And we're told the proportion, so there's 3 machines, machine A, machine B and machine C. We're told the proportion of components made by each machine that are faulty. So 10% of all of the components that are made by machine A are faulty, 5% of all of the components made by machine B are faulty, and 1% of all the components made by machine C are faulty, okay? And And we were also told the proportion of each of the components made by each machine. So 50% of the components are made by machine A, 30% are made by machine B, and 20% are made by machine C. And we need to find, well, what's the probability that a randomly chosen component that's chosen to be faulty was made by machine A? Well, let's get there. Let's first of all set the question up. So first things first, I'm going to set up my tree diagram. Okay, so I'm going to choose which way around I'm going to do this. Okay, I am going to put the machine on the first set of branches. So I need 3 machines, so therefore I need 3 branches. Okay, so I'm just going to draw myself 3 branches. So this could get slightly messy, but let's see what we can do. Okay, so these are going to be the machines, and this is going to be machine A, machine B, and machine C. Okay, so what information am I given? Well, let's look at this. This is the thing which I'm interested in, okay? So this is the proportion of components made by each machine. So I know 50% are made by machine A, 30% are made by machine B, and 20% are made by machine C. So I'm going to put those percentages on my branches. So 50% are made by machine A, 30% are made by machine B, and 20% are made by machine C, okay? Then I'm going to go back and actually fill in the faulty or not. Okay, so if they're faulty, they've got 2 options. You can either be faulty or not faulty. So basically, for each machine, they either make a faulty component or not a faulty component. So I'm going to go faulty and then F with a dash. F with a dash means it's not faulty. And I'm going to do that for each machine. So faulty, not faulty, faulty, and not faulty. Okay, fine. Now I need to fill in the proportions. Well, look, I'm told that 10% of all of the components made by machine A are faulty, which means that there's a 10% chance it's faulty and a 90% chance that it's not faulty, given it was made by machine A. So this is the probabilities up here, okay? There's a 10% chance it's faulty, given it's made by machine A. So I'm looking at this here. And a 90% chance that it's not, okay? Let's keep going. So the next one is 5% were made by machine B are faulty. So 5% were faulty and 95% weren't. 95% were totally fine. And then finally, 1% of all the components made by machine C are faulty. So you got 1% down here and 99% here. Okay, good. So I've filled out my tree diagram. Now let's actually answer the question. So let's do part 1 first. So I'm given that a component is found to be faulty. That's what's given in the first line. So I've been given that information. So I've been given it. A randomly chosen component is found to be faulty. So that's given. Find the probability that the component was made by machine A. So in other words, for part 1, I want to find the probability that it was made by machine A given it was faulty. Okay, because I'm given that information. It's not just what is the probability that this component was made by machine A. I'm given that extra information. Okay, I'm given the evidence that the machine was faulty. So therefore, in order to do this, I can remind myself of Bayes' theorem. Okay, so Bayes' theorem is basically saying probability of A given B should be equal to the probability of B given A times by the probability of A, all divided by the probability of B. Okay, now this is a formula which you're going to get very practice with. So by the time that by the time we finish this kind of section, you should have this formula pretty much committed to memory. So I'm just going to move this over here to make it easier to compare. So let's move you over here. Okay, so basically what I'm saying is that A is machine A and event B is whether it's faulty or not. So using this, I should be able to say, well, okay, the probability of A given it's made by machine A given it's faulty should be the probability it's faulty given it was made by machine A times by the probability that it was actually made by machine A, that's your prior ratio, all divided by the probability that it's faulty. Okay, so let's work this through. Okay. So if we work this through, I first of all need to find the probability that a component is faulty given it's made by machine A. Okay, well that probability there should just be the 10% up here. Okay, you happy? Because that probability represents it's faulty, but it was made by machine A. Not by machine B, not by machine C, it was made by machine A. Okay, so I'm looking for 10% to go there. So this is going to be 10% there. Okay, then I'm looking for the probability that the component was actually made by machine A in the first place. Well, the probability it was actually made by machine A in the first place was 50%, because that's the proportion of components that were made by that machine. So I need to multiply that with 50%. Now I need to find the probability that it's actually faulty in the first place. So I need to find all the ways that I can end up with a faulty component. So all the ways that I can end up with a faulty component, either it was made by machine A and it's faulty. So either it was made by machine A and it's faulty, in which case that's going to be 50% times by 10%, or it's faulty and it was made by machine B. That's going to be 30%, because 30% of the components are made by machine B and 5% end up being faulty. Okay, or it's faulty and it was made by machine C. So therefore 20% of the components are made by machine C, and there's a 1% chance that that is then goes on to be faulty. So I need to add all of these probabilities together. All right, then, so it's going to be 50%. In fact, what I'm just going to do is just multiply them together up here, just for the sake of simplicity. Okay, so 50% times 10% is going to be 5%. Okay, so there's a 5% chance there. Then 30% times 5%, well, that's going to be 0.3 times by 0.05. That's going to give me 1.5%. And then 20% times by 1%, that's going to give 0.2%. Okay, so 0.2%. So I just need to add all these probabilities together. So it's going to be 5% plus my 1.5% plus my 0.2%. Now I'm in a position where I can stick all of this into a calculator. Okay, so I'm going to bring up my calculator now. Here we go. I'm just going to stick all of this into my calculator. So first things first, I am going to start by typing my fraction. So I get my fraction here. Okay, on the numerator I'm going to get at 10%. Well, I'm just going to be lazy. I'm just going to convert all of this to decimals rather than like typing percent all the time. So 10% is 0.1, and I'm going to times that by 50%, which is 0.5. And on denominator, so remember, press the down arrow, I want 5%, which is 0.05, plus 1.5%, so 0.015, plus my 0.2%, which is going to be 0.002. If I press equals, I get myself my probability, which is 75%. Okay, so that's going to be approximately 75%, or I'm going to write it as 74.6% actually. Okay, so hopefully that makes sense. So for part 2 then, I need to find I've been told that a randomly chosen component is found not to be faulty, so not to be faulty in this case. Now find the probability that was made by machine A. Well, I'm going to do this longhand and then I'm going to show you how you can do it slightly quicker in just a second. Okay, so first things first, I'm told that it's not faulty and I want to find the probability it was made by machine A. In other words, I want to find the probability that it was made by machine A given it's not faulty. Well, just using Bayes' formula, that should be the probability that it's not faulty, given that it was made by machine A, multiplied by the probability that it was actually made by machine A in the first place, all divided by the probability that it's not faulty. Okay, so divided by the probability it's not faulty. Okay, so let's work through this then. So the probability that it's not faulty, given it's made by machine A, is going to be 90%. Okay, so 90% of all the components made by machine A are not faulty. So I'm going to put 90% there. Then I'm going to multiply that by the probability that it was actually being made by machine A in the first place. So that's going to be 50%. Okay, it's going to be 50%. And then I'm going to divide all of that by the probability that it's not faulty. Well, the probability it's not faulty, just remember, okay, to work that out, it's going to be this times this, so 50% of 90% is going to be 45%, okay? And then this probability here is going to be 30% of 95%, which is going to be 28.5%. So just remember, I'm just multiplying probabilities together here. I'm not writing them in because we're running slightly out of space and time. Okay, and then finally, the last thing that goes down here is going to be 20% times by 99%, which is 19.8%. Okay, then I just need to add all those probabilities together. So 45%, do it in red, 45% plus 28.5% plus 19.8%. I'm going to stick all that in your calculator. I'm not going to do it on the screen. I'm just going to do it very quickly now. And we should get 48.2%. Okay, so 48.2%. Hopefully if I haven't made any mistakes, that should make sense, okay? So just be aware, okay, it's not quite as simple as just finding the complement. So you think, well, okay, you know, first question was basically saying, what's the probability that it was made by machine A given that the component is faulty, okay? That was about 75% chance. But then I asked the question, well, okay, what's the probability it's made by machine A given it's not faulty? Some of the sort of, you know, the shortcuts, you know, which you've been shown in the past, you just have to find the complement because it's basically the opposite situation. Except in this case, it's not the opposite situation because you have to take into account that there are 3 other machines there, okay? 3 other machines there. So just something to be aware of, okay? But effectively, that's how to work that out. Now, in terms of what I want you to complete for homework, okay, I want you to have a go at this question here. Okay, so please can you complete this question here? Okay, so candidates have to complete a driving test. So a driving exam consists of 2 tests. You've got a theory test and then you've got a practical test, and the theory test comes first, then you've got the practical test. Candidates must pass the theory test before they take the practical test. Okay, so you must pass that theory test, but you can take a test multiple times. Okay, so basically you can take a theory test as many times as you like, but you must pass it before you can go on and take the practical test. So you can take a theory test 100 times if you want to. Now, this is interesting. This question is interesting. The number of people or the proportion of candidates that pass on their first attempt. So you're basically told that 60% of candidates pass the theory test on their first attempt. Okay, and then 80% of candidates that pass the theory test on the first attempt also go on to pass the practical on their first attempt. Now you might be sitting there going, well, hang on, how is that possible? So, you know, people who don't pass the theory test, they can't go on and pass their practical test. That's not true, okay? So yes, you must pass the theory test, but remember that this is talking about, the reason why it's not true, this is talking about the number of candidates that pass on their first attempt, okay? So you're only interested in candidates that pass on their first attempt here, okay? And you're basically saying 75% of candidates fail both tests in their first attempts. So basically what I would encourage you to do, first of all, start off by creating a tree diagram here, okay? Or do it however you want, but I would encourage you to do a tree diagram and then go on and answering these 2 questions here. So first of all, find the probability that a candidate selected at random has failed the practical test in their first attempt. And then if a candidate selected at random has failed the practical test on their first attempt, what's the probability that this candidate has passed the theory test in their first attempt? So can I ask you to have a go at that question there? I'm going to require you to upload that question to Flipgrid for me. Okay, so please can you upload that before the next lecture? So thank you very much.